This lesson is going to look at the chi-squared test called the goodness of fit test. So first we're going to look a little bit at the chi-squared distribution. So the chi-squared distribution is a continuous probability distribution, so in some ways similar to the normal distribution and the t distribution, the student t distribution we talked about earlier. If you look at that distribution in our formula sheet, you'll see that it looks similar to those, but this one's not quite as symmetrical. We say that this one's positively skewed. It's a little lopsided. It gets less skewed the larger our degrees of freedom that we're looking at, but it is still skewed. Another difference that this one has is when you look at this table compared to our normal distribution, this table is always done with the right tail. Our normal distribution always had that left tail. So there's another significant difference when we get around to using the table. So something to keep in mind. The value of chi-squared on that one is never negative, so we're not looking at z-scores on these ones. We calculate chi-squared quite differently. We'll get to the calculations in a moment. And as with our normal and t-distribution, the area that we're talking about under the curve is corresponding to a probability, and because of that, our total area under the curve is also going to add up to 1. So that's the same as our normal distribution. So the goodness of fit test, where we use this chi-squared distribution, uses something called a multinomial experiment. So that word multinomial may look kind of like another experiment we talked about earlier in the course, which is the binomial. So if you look at the difference between the multinomial and the binomial, big difference there is that prefix. So the binomial had two possible outcomes. The multinomial experiment has more than two, right? That's what multi means, multiple. So going to jump down to condition 3. Each trial will result in exactly one of k, right, where k is some number, possible outcomes. So instead of two possible outcomes like we had in the binomial, we now have multiple possible outcomes. The other parts here, though, are just like the binomial experiment. So we have n identical trials. Each trial is independent. The probabilities of the k possible outcomes are constant. All of that is exactly what we had in our binomial. So your textbook uses this particular notation for our goodness of fit test. It's pretty standard. The things that change a little bit from other texts, so if you are looking online at some other resources, you may find the observed and the expected frequency use some other notation. The text we used last year used a different one, so if you have a friend who was in this course last year, they might have something slightly different in their notes. But this is mainly how it looks. So pretty similar again to binomial, and for the number of trials, p for the probability. Different from the binomial, we have subscripts rather than p and q. Expected value in the binomial was n times p, right? Our mean was n times p. Well, our expected frequency is also n times p. So that's the frequency we would expect if our null hypothesis is true. So if it does meet some claimed distribution. So our hypothesis test is kind of similar to our other hypothesis tests and the steps that we do. I'll talk about those in a moment. But what's different is we're always going to have the same format for our null and alternate hypothesis. So the null hypothesis is always going to be that the proportions are the same as some claimed value. And the alternate hypothesis is going to be that they're not the same or that they're different. Calculations for this is a little different, so we're going to use this formula to calculate our test statistic known as chi-squared. I mentioned last class that that chi-squared is a Greek letter, so although it looks like x squared, it's actually chi-squared. Critical values we get from that table we mentioned. So our degrees of freedom here is a little different. It's k minus 1, which stands for categories minus 1. So we use k for the number of categories in stats. Not C as you might expect. It's as though we can't spell. Our significance level is same as before, alpha. So typically small values like 5, 1, 10%. And in this particular section, all our tests are going to be right-tailed, which actually is kind of nice because remember, looking at that chart, it gives us values that are right-tailed. So we're going to be using the values straight out of the chart, which is kind of handy. In order to apply this distribution, right, we can only use it if we have fairly large samples. All frequencies have to be at least 5. So if our samples are smaller than that, it's not good enough to say we can apply that distribution. So our steps for these hypothesis tests, pretty similar to our other hypothesis tests. Start up by writing our null and alternate hypotheses. This time it's either the data fits the distribution or it doesn't fit a distribution, so it's a little easier in that sense. Calculate our expected frequency for each class. So using that n times p. Calculate the test statistic using our test statistic formula here, so the sum of the differences squared divided by the expected frequency. Calculate the degrees of freedom, so based on our categories, look up our critical value. And then our decision step is the same as before, reject or not reject depending on whether the test statistic falls in the critical region. I probably should have put a step 6 here, which is to write a statement, because we always do need a statement. Not letting me put a 6 in there. Ah, there, it reappeared. And remember that conclusion should address your original question. So our first question here, we have a publisher wanting to give out gifts to attract new subscribers. And in order to test, are these going to be equally attractive? They take a sample of 60 subscribers. 17 of them chose gift A, 21 chose gift B, 22 chose gift C. So is this enough evidence to say that they're going to be equally attractive? In other words, if they're going to go about ordering these gifts, should they order equal numbers of them? So this equal is something that fairly often shows up in these questions, not every time, but it's something that we need to pay attention to because it's actually telling us our proportions. Right? We're being asked if the proportions are equal. So that's our null hypothesis. So if we have 3 categories, A, B, and C, those proportions are all going to be 1/3. Our alternate hypothesis is then that they're not equal. So in this particular question, other things to identify, our 60 is our n. The numbers that we have in each category are going to be our observed frequencies, and our alpha is 0.05. So I have this one set up as a table. These questions aren't typically given as a table, but often we set up a table to answer them because we're going to have some of these repetitive calculations. So I put up the table so we have our categories, we have our observed frequencies, we have our expected frequencies. I could have this table completely flipped from how it is. I put in 2 optional columns. For this first example, I'm showing them both just because some people like to show every detail of their calculations. So as you go through and pause and try the calculations, you can make sure you're getting those numbers. I don't tend to show them after this first example because they really aren't required. And our last column is to do that test statistic calculation. We're going to need the total of the differences between our observed and our expected squared divided by our expected. So for our first category, we've got this proportion is 1/3, our observed frequency is 17. So when we calculate our expected, we use this n that we had for the total. Now, a common mistake people make is to use their observed frequency as n. Don't do that. The n is always the total of all the frequencies, not the number for the category. So our expected frequency for all 3 of these, because they do have equal in our null hypothesis, is going to be 60 times 1/3, so 20. So to do this calculation, we need the difference between our observed and our expected. So 17 minus 20 gives us -3. We square that, we get 9. And then our last step, we divide that 9 by our expected frequency. So this is 9, maybe we'll put that in there, 9 divided by 20 to give us that 0.45. So I suggest you pause, do the next two rows yourself, so it's a little more than 2 calculations, and then check and see if you got the right answers. Now the totals here tell us a few different things. So the total of the observed column should add up to our n, makes sense, but so should the total of our expected column. So lots of times some of these expected frequencies we end up having decimal values, in which case your number may not add up perfectly if you have some rounding errors, but it will add up very, very close, right? It should be within however many decimals you kept. The optional columns, the observed minus expected squared doesn't really tell us anything as a total, but we know we're on the right track if the observed minus expected before we squared it adds up to 0, right? Because it should add up to 0. Some are going to be above the expected value, some of them are going to be below the expected value. Makes sense. And this last one is our test statistic, because if you remember the formula, and I'll just scroll down so we have it on our screen, right? It's the sum of all of those calculations. So we add those up, we get our test statistic. So 0.7 in this case. So the other thing we need besides our test statistic is our critical value. So we're going to use our table. And we need our degrees of freedom is k minus 1. So k, remember, is our number of categories. We have 3 categories. So our degrees of freedom is 2. Alpha was given in the question as 5%. So we go over to that table. And we're looking at the 5% column and 2 degrees of freedom. And we see that works out to 5.99 for our chi-squared value. That's the critical value. So remember, looking at that from do we reject the null hypothesis perspective? I'm going to go back to where we have our diagram. So the 5.99 is our cutoff line here. Our test statistic was 0.7, so that's going to be somewhere over here. Because remember, this doesn't go into the negatives. So we're nowhere close to our critical region. So we would say do not, right? We're not in the critical region. Do not reject the null hypothesis. And our conclusion should say there's not enough evidence to reject the claim that they're equally attractive. So same kind of wording that we used in our other hypothesis tests. Example 2. So we have greenhouse gas emissions by sector, and we're given what they are for the nation. And the question is, does a particular province have the same breakdown as the nation? So our claim is that they're the same as they are nationally. The alternate is that they are different than they are nationally. So this time they're not the same as each other. There's some very specific values. So 32.2% for the first category, 29.4% for the second category, and so on for the rest of our categories. So if we look at this, our observed frequencies are going to be the values from these 300 emission sources. So our n is 300. We should maybe write that one in. Word always wants to capitalize. And our first observed is 102, second is 88, third is 37, and so on. Alpha is 5% again. So we do this calculation for each one of these. So this time it's going to be a little more work for 2 reasons. One, we have more categories, and 2, we don't just have the same proportion each time. So we're going to have to multiply our n, that 300, by the corresponding percentage. So I put my percentages for each 0 just right into my table. So 300 times 0.322 gives us 96.6. So here's one where we're ending up with some decimal values. I didn't leave those, I left those 2 columns blank in my example here. You do have them in your sheet if you want to calculate the difference between the two and then square it as a separate calculation. And then we divide that value by our expected, so in this case 96.6. But you can do this whole calculation all at once, so there's not really a need to write down those individual steps. Again, pause the video a moment, check that you're getting the same answers all the way down the table. So our totals n should add up to the total in our sample. Our total here should also add up to the total in the sample. So because I did some rounding, it's off by a tiny little bit. So that's within an acceptable range. And again, we've got our test statistic down here, because that is our sum of those calculations. So this time, degrees of freedom, we have 5 categories, so 4 degrees of freedom. Alpha in our question was 5%. So let's look at that. So let me scroll up a little bit here, and then we'll look at that on our table. So 4 degrees of freedom, 5%, so this time we're looking at 9.49 for our critical value. So again, our test statistic, nowhere close to our critical region. We're going to not reject the null hypothesis. There's not enough evidence to reject that the percentages are the same for her province as for the national values. The way this question was worded, you could have also said there's not enough evidence to show that her province is significantly different. Ultimately, on these questions, we're concluding they are different or they're not significantly different, right? So if they're not significantly different, it's kind of the same as saying they're the same. So that's where we're going to stop with these examples. So you definitely have some more in your book. This is the old book though, so look on your sheet that I have posted to get those examples.